So now the next topic is symmetry. And so the original formula is defined as let's go. Let's see a little space here. So you define as the original formula is like 0 to 2 pi, 0 to 2 pi, or minus pi, or pi to minus pi. Doesn't matter which you use. So go back to this minus pi to pi. If you have function defined over this domain minus pi to pi, right? Then you can use the original formula. You can change it all back to just choosing L equals pi. You go back to the old formula. Okay, you can use this the original form of Fourier series. So basically, you have a function, whatever the function is, right? And effectively, you're just saying that to use this formula after you do the expansion, basically you are extending this to a periodic function. Except that even if this function doesn't look like a periodic function at first, you generalize that to a periodic function, there will be a jump at the boundary, say pi to minus pi to pi, that to extend the periodic function becomes something like that. And there's a jump over at the boundary. But this doesn't matter if you just, what your concern is just to do expansion within your domain, then it's fine. Except this the expansion may not be very good at the end, at the discontinuity. You need a very large number of n to get a good approximation. Okay, so that's how you use the original Fourier series. But assuming that if this function that you want to assume, I mean, this is like a consideration. Later on, we will actually put in a different language. So assuming if this function is not just a general shape, if it is even or odd with respect to 0, even means that fx is within this domain. So this function is like that, so something like this, something that right, that becomes even, right? And obviously, when you put in this formula or that formula, it's better to use this the cosine and sine to do this discussion, right? If you use if f is even, then obviously the cosine is even, sine is not, sine is odd. Then you can convince yourself that the order dn will be 0 because of dn. If you go back to the formula. If f is an even function, sine is an odd function, you multiply even function with an odd function, is still an odd function, and you integrate over a symmetric range, then this is bn's must be 0 in this case, right? This is 0 for even n. Even f, not just even f. Okay, and likewise, if this is odd, if the f is actually odd, so you set like that, something like that. If it means this is even, odd means you have a negative sign, right? This is even, this is odd, right? Then obviously, a sub n, all the a sub n will be 0. It's because you multiply by cosine. Right? F is odd, cosine is, all these cosines are even. This product is odd, and then you integrate over symmetric range that is n is 0. So for even f, This is for odd. And for even f, you just keep all the a and b, all the b's at 0. For odd f, all the a's are 0, only b, right? So in that case, you can say even f, you get a Fourier cosine series. For odd f, you have a Fourier sine series. It's okay. So that's how you get part of that, right? So this is the discussion how you get the series, something like that. But in practice, sometimes you just don't care about this. This saying that you define a function over 0 to pi. But this is the base case. Right? You can also define this from 0 to L. You just after all the discussion, you just rescale, just like what we did here. Just rescale it instead of 0 to pi, you rescale 0 to L, and you just basically you just call your domain 0 to L, or 0, and then we define it. We scale it to 0 to pi. So you define the fx over this way, right? Then you can either use the cosine series or the sine series, right? And get your expansion that way. So basically, the idea is this f might be arbitrary over here, right? Just like what we had before. For the cosine series, basically you're saying that to do a cosine expansion, basically you imagine you extend this function to the negative x by refraction, symmetric refraction. So basically just extend it to the negative x direction and following the even function rule. And then going back to the original Fourier series expansion, you get a cosine series this way, right? Then that is allowed. Then you get a Fourier cosine series. Fourier cosine series basically keeping all this just the cosine and all the a term, and then the just the a-n's are using this form, except it's not 0 for this case. And sometimes you can rearrange that for this case because it's symmetric. You assume f is extended to like, although it's defined from 0 to pi originally, you extend it to minus pi to 0 also. So this is for the Fourier cosine series a sub n, although a sub n will be, you just keep half of that the integral and multiply by factor 2. Right. You can do that. So this is for the cosine series. You just choose all the a sub n this way, right? And then you just expand that function over 0 to pi using this expansion, keeping only the a sub n, and use the cosine or the cosine term. And likewise, you can use the sine series. So now you imagine you are not extending it in symmetric way. You extend it in anti-symmetric way, follow this rule. So basically negative of that. So imagine you refract it and then take the negative sign. You get this function, and if you use the original Fourier series formula, all the a sub n becomes 0, only keep the base b sub n. And likewise, b sub n now defined as the integration of the function over 0 to pi multiplied by sine n. So sine x, nx dx. Okay, right? And that's how you get the Fourier sine series using all these coefficients. All right. So basically, now you go back to the original idea. So if you have a domain defined over a finite range, a finite domain, a function defined over a finite domain, you can do expansion 3-way after we learn all this. You can use the full Fourier series using both sine and cosine, and that you get one kind of expansion. You can use part of that. You can use just the cosine and do a Fourier cosine series. And then finally, you can do just keeping a sine and do a Fourier sine series. You can have 3 kinds of expansion. And those are all valid if you want to expand your function over just this finite domain. Okay, is it confusing? That this expansion, you are free to choose either one of them, either one of them. But in practice, they have different use. So, in principle, you can do, and I think there's an example in textbook saying you can expand like a linear function x in all different way, right? And that's allowed. And but in practice use, you ask the question, why do we, or when should I use the Fourier cosine series or Fourier sine series? You can ask, although both, you can use both, either one of them, but one of them will be more convenient for some problem than the other one, right? And for us, the most common case is when you have a function that is defined with a boundary condition. Say, sometimes you have a function f defined over this finite domain that the endpoints are zero. So whatever how we fluctuate, we end up to zero. Right? If both n are zero, and obviously you want to use a series that is more convenient, right? So in that case, if we use a sine series, remember this way explicitly going back to nx. It's cosine nx. Right. Right. If it's from 0 to pi, you want the function satisfy a boundary condition that is 0, f is 0 at both ends. I mean, the sign already satisfied all these, all the two conditions. When x is 0, or the sign is 0. When x equal pi, sine n pi is 0 for all integer. So it's much better to use the sine series because it satisfies the condition that you want automatically. Instead of the cosine series, you can use the cosine series, but then you end up to satisfy the condition that f is 0 at both either end. Then a non-trivial constraint over all your a n, right? Because like when you evaluate 0, all these are 1. You're summing over all the a n, it has to be 0, which is a condition you can satisfy, but it's not a cumbersome thing to do. You don't want to give too many constraints over your coefficient. Otherwise, when you do all the later manipulation, that becomes cumbersome. You always need to carry the constraint and all that. It's much better you use just the Fourier sine series. And because this expansion, either using cosine series or sine series, either one is a complete expansion. You can show that they are complete individually. The Fourier sine series is complete, Fourier cosine series are complete. And using our completeness condition, say you can use just the sine or cosine. They also satisfy the completeness condition for just using sine or cosine. Okay, and so if your problem has a constraint like that, then you use a Fourier sine series. The boundary condition is set to be 0. But in some cases, the boundary condition is not on the function; it's on the derivative. Like instead f is 0 on both ends, you can have f pi equals 0 at x equals 0. Right? If the derivative is 0, then what you do? You use cosine, right? Because all the derivative of cosine, including the constant, the cosine derivative becomes sine, and that's the same consideration. That's all this derivative of cosine at sine is 0 at pi. Okay, so you automatically satisfy the derivative condition. The boundary condition is derivative, and uh, in the language that we use later, the derivative is 0 condition. Boundary condition, what we call is the Neumann boundary condition. when the function itself is zero on the boundary, we call it a Dirichlet boundary condition. Okay, so depends on the problem that you might want to use a sine series or cosine series respectively. Yeah.
If it's not at zero, if it's something like 3 pi by 4, something like that, can we add a base to sine or cos?
That you probably want to rescale it, or we define your function so that you go back to either one of these cases. You have a more particular boundary condition because you need to figure it out more specifically. Like if you have a special case, a boundary condition, like if you have mixed boundary condition, obviously that becomes complicated. You might need to end up going back to use the full condition, and you cannot take advantage of this set it to even or odd function. But that it depends on the specific problem that can be complicated, right? And finally, what is more convenient to use the full Fourier series is if your problem originally is periodic in itself. So if you have a periodic function that physically is periodic, like if you expand your function of the azimuthal angle always goes 0 to 2 periodic, right? Then obviously you want to use both series, right? You want to use either the exponential functions or use both sine and cosine, and that becomes more convenient instead of using either sine and cosine. Is okay? Although all three expansions are complete series, complete expansion, you can do any of that, but in order to satisfy the specific condition of the problem, we choose either one of them to use. Question? No? Okay. All right, so that is Fourier science. And likewise, you can rescale the just like what we said. This is CO to pi, but if it is CO to L, then you go back to this multiplied by pi divided by L. You can use the sine series n pi x over L. This becomes n pi x over L, right? And then then you can use all this formula. Okay, there was an example that again, this example of the integrals are fairly elementary. You could figure that those out. And the next topic is operation. So once you have that expansion, you can do some other operation like integration term by term. If you want to integrate f, you can use the function series expansion to do the integration term by term. That's fine. Integration is easier to do, and usually not having much. The other kind of operation is taking derivative, and that can be a little bit problematic. Say, you take derivative of all these functions, you take the derivative of the basis, will give you a factor n out. When you take one derivative, you put it, because exponential, when you take the derivative, you pull out the factor I n pi over L after you rescale it. So you have the proportion to n, right? So the series becomes more difficult to get convergent because you have extra n. When you think about your ratio test, you get extra n in the factor, and that becomes when n is large, becomes larger and larger. Coefficient becomes larger and larger, and physically you can say if your original f has a derivative, you already have a derivative discontinuity, then taking a derivative obviously is not defined over. That becomes a infinite derivative. That's not defined. So taking derivative is a little bit tricky. So you need to be a little careful. Look at the function itself before you say you can take derivative individually. Okay.